Hi, today we're solving problem 44. Pentagonal numbers are generated by the formula p sub n is equal to n times 3n minus 1 divided by 2. The first 10 pentagonal numbers are 1, 5, 12, 22, 35, and so on. It can be seen that p4, so the fourth pentagonal number, plus the seventh pentagonal number, which is 22 plus 70, is 92, which is the eighth pentagonal number. But their difference is not pentagonal. We need to find a pair of pentagonal numbers so that their sum and difference are both pentagonal, and the difference is minimized. And we need to find that minimal difference. So for this problem, we're going to first generate all of the integer pentagonal numbers that fit within a Scala integer, and then we're just going to iterate over possible values of these pentagonal numbers and check if their sum and difference are pentagonal. So let's switch over to IntelliJ. The first thing I'm going to do is implement a method to generate the nth pentagonal number. So I'm going to do def pentagonal. It's going to take n of type int, and we're just going to use that formula. So here we have n times 3 times n minus 1 divided by 2. So we can test this out. We can print pentagonal. Let's do the third one. So we should run this and we should see 12. And it works. So now we know this formula is correct. Let's move on. And now next we're going to calculate all of the pentagonal numbers which fit inside an integer. So I'm going to do val is pentagonal. And the reason I'm calling this val is pentagonal is because later on we're going to use this variable as if it were a method to check if a number is pentagonal. But we're going to back this way of checking with a collection. So what I'm going to do is I'm going to create an iterator, and I'm going to start at 1 from 1. So now this creates an infinite iterator starting from 1. Now I'm going to take each value and get the pentagonal number. So these represent the indexes of the pentagonal numbers. I'm going to take this index and calculate that pentagonal number. Now I'm going to take the ones that are greater than or equal to 0. Now the reason I'm doing this is because at some point we're going to run into integer overflow, and pentagonal is going to return us a negative number. But we only want the pentagonal numbers that fit within an integer for this problem, so I'm going to take while the number is greater than or equal to 0. Now, the way we're solving this problem isn't actually guaranteed to be correct. It does work for this problem since we're setting a high enough bound, but really, if we wanted to solve it the same way, we would have to go up till infinity, because we don't know when we have the minimum value. You can do a few tricks like checking if the minimal distance is smaller than the minimum distance you found globally. So given a p sub j, you know what the minimum distance to p sub k must be, and you can check if that's under the minimum distance you found so far, but even that is too slow. So we're just going to stick with an integer upper bound, and that does give us the correct answer. So here we're keeping only the integer pentagonal numbers, and so that we can quickly check if a value is in this set, we're actually going to convert this to a set, and this gives us a set of integers. So then when we want to check, we can just do is pentagonal, and we can check if 12 is a pentagonal number. And if we look at set.apply, we see that it actually just calls contains. So using apply on a set checks if the number is part of that set. So if we can run this, and we get true. So now is pentagonal is correct. Now all that's left is calculating the minimal d value over all possible pairs of j and k. So I'm going to start by setting a variable, and this will be a mutable var here, min difference. And we're going to start this out at int dot max value. So this gives us the maximum value we can have for an int. Now what we're going to do is we're going to first iterate over the index. So this is the value of j. So we're first going to iterate over values of j. So I'm going to start out at 1, and I'm going to go all the way up to is pentagonal.size. Now the reason I'm doing this is I know that the largest index of the nth pentagonal number is just going to be is pentagonal.size for integer pentagonal numbers. So here we have all of the pentagonal numbers that fit within an integer. So calling is pentagonal.size gives us the largest index that would produce a pentagonal number that fits within an integer. So we're going to iterate over those. So I can actually do a for loop here. So for j in this one, or actually I'm going to do I1. So this is the index of the first number. Now given the index of the first number, we can calculate the first number, the first pentagonal number. So I can call this num1 is going to be pentagonal. Actually, let's call this p1 because this is a pentagonal number. And pentagonal at I1. So this gives us the pentagonal number at the I1 index. Now we need to iterate over all possible values of k. So first I'm going to create val num2s. So we're going to calculate all of the possible second number. So I'm going to start with I1 minus 1. So this is the index right before the index that we picked for the first number, because for k we're going to pick an index smaller than I1. And I'm going to go to 1. But since we're going in reverse order, I need to tell Scala that we're doing that. So I do by -1. Now on this range, I want to get the pentagonal number. So I'm going to map each of these indexes to the pentagonal number there. Now what I'm going to do is I'm going to take these nums. I'm going to first do a take while. So I have all these pentagonal numbers, but I can do an early check to make sure that the difference between pentagonal 1, and we should actually call this P2S. So we're given a second number, but we can quickly terminate when the difference is greater than the min difference we have so far. So I can do take while, and we take the second number and we do P1 minus P2 has to be less than the min difference. So that's how long we want to take. And we can replace that with underscore. And we know that once it's equal to or greater than min difference, all successive P2s will also be that. So we can do a take while instead of a filter. Now on this take while, we want to filter the ones, or actually find the one such that given P2, the sum and difference have to be both pentagonal. And we want to find the highest value of P2 because that gives us the smallest difference between P1 and P2. So that's why we're doing find here, because that gives us the first element of P2s that satisfies the property, and we know that will be closest to P1. So given P2, we need to check that is pentagonal P1 plus P2, and the difference must also be pentagonal P1 minus P2. Now that we've found this option, so find is going to give us an option of integer, which is what is the P2 value that satisfies this. If the value does exist, we want to set min difference to be our new smaller difference. But how do we get that value out of the option only if it is defined? Well, we can just do a for each. So this is as if we're iterating over this option, and the function that we pass will only be called if the option is defined, and it'll be called with the value of the option. So we can take P2 here, and we can set min difference to be P1 minus P2. Now, at the end, all you want to do is println min difference, because that'll be set to the smallest difference we found. Now we can run, and we can wait. And we get our answer. But that was pretty slow. I mean, if we run again, we can count now. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi, 6 Mississippi. Okay, so it's somewhere between 6 and 7 seconds. And that's pretty slow. Let's take a look and see if we can make this faster. Now, where are we spending the most time in this program? It's here. For each of the indexes, we're also going over all P2 indexes. And for each of these, we're first calculating all of the pentagonal numbers, so that creates a new collection. Then we're doing take while, creating a new collection. And then we're doing find and for each. Now here, we're first of all creating collections at each step of these. And all of these operations could be combined into one operation. So we don't need a map and then do a take while. We could just combine those into one iteration over this range. Now with Scala, keep maintaining this approach of chaining these functions on our collections is really nice, because now we can just see each step that we're doing, but we're getting a performance hit because of that. But in Scala, we can do .view, and this allows us to efficiently chain these functions. Now we can run with this .view, and we get our answer almost instantaneously. So now we're getting a much faster, so now it's taking about a second, so that's a 7 times improvement. Now what is view doing that's making it so much faster? When we call .view, we get back a sequence view, and views are lazily evaluated collections. So what lazily evaluated means is that this collection is going to be lazy and not calculate anything until it really needs to. And what is this really needs to? Well, that's when we called find. So when we call find, this is going to return us an option of int, and at this point it actually needs to give us a value. But until then, when we call map, it says, okay, I'll do a map, but it actually doesn't do a map. It just stores that when I do calculate a value, I should be running a map. And same with this take while. It doesn't actually do a take while. It just says, when I do need to calculate a value, then I will be doing early termination. So when we calculate find, what it does is it first checks the first value, it maps it, it checks that it satisfies this property, checks that it satisfies this property. If it does, then we just return immediately and we don't calculate any more values. Otherwise, then it continues on the later values. So we're getting a much faster answer here. And that's it for problem number 44. So here we don't have a perfect solution. We are looking at only the pentagonal numbers that fit within an integer, and I haven't been able to prove to myself that this value that we find that's an integer pentagonal must be the answer, because we don't know what we might find later on. And there's actually some interesting solutions out on Stack Exchange. So maybe in the future I'll explain one of those solutions. But for now, we have a solution with integer pentagonal numbers, and we're done. So I'll see you next time when we solve problem 45.